Okay, so let's continue with our fat characterization section, and let's try to remember a little bit what we talked about last time. Okay, I didn't start the chat box. Let me start it here. All right, I only have few of you here, very few, but let's be active on the chat then. All right, so what is the importance of fat characterization? Can you give few examples we talked about last time? Oh, they're trickling in. Shelf life stability, quality control or quality assurance, food safety, labeling, palatability and sensory. Very good. You got it down. All right. So many different reasons we characterize fat. We characterize the different components of fat. If you have monos, monodiacylglycerols versus phospholipids versus saturated fatty acids, unsaturated fatty acids, cholesterol. So the different components that need to go on the label, you have saturated fat, cholesterol, trans fat. So these components need to go on the label. So we do characterize them or quantitate them. We also need to determine shelf life based on the different types of fats we have. Do we have a polyunsaturated fat or more saturated fatty acids? So, and we look at safety. We have secondary metabolites of oxidation, some of them have toxicity, such as malonylaldehydes or cholesterol oxides. So we look at that too. And determining, let's say, the processing, the efficiency of processing, such as refining, we can determine that if we have high percentage of free fatty acid, that could be due to not proper refinement of the crude oil. If we have a hydrogenation process and we determine a degree of unsaturation and we don't see a reduction of degree unsaturation, or we still have some unsaturated fatty acid, that means the hydrogenation was not done properly. And then winterization, we look at formation of cloudiness or precipitation of the waxes. So by winterization, what we do during processing is we reduce the temperature, waxes will precipitate, you have clear oil. So a lot of different things. We talked about impact of processing, shelf life, nutrition labeling, impact of using frying the oil or not frying the oil, using the same oil multiple times for frying that will generate free fatty acids, then potentially secondary oxidation products will make it toxic, and so on. So many different reasons for fat characterization. Okay, so we'll go over a few here. Yeah, determining packaging type is really important too. I see in the chat because the permeability of oxygen can be a potential for enhancing or reducing lipid oxidation. Okay. All right. All right. So I'm going to move this out of the way now for a second. All right, so we have so many different analytical methods that we will be talking about today. And there are a set of methods that we usually use for bulk fat or oil. What do we mean by bulk fat and oil? That means either olive oil or yard or butter. So just oil or lipid or fat. We do a lot of different testing there. There are physical characteristics that we'll talk about. There are a couple of few methods that we do specifically for bulk oil, for example, iodine value to determine degree of unsaturation, saponification value, which is an index of the average molecular weight of fatty acids, and the free fatty acid content, which is an index of either refinement or what we call hydrolytic rancidity, when the lipid breaks and gives you free fatty acid. And also it relates to the age of the oil you use for frying. So we will be doing iodine value, saponification value, and free fatty acid analysis in the lab next week. We're also going to do some lipid oxidation testing in the lab, which is measuring the primary oxidation products, which are peroxides. So measuring present state, that means you have an oil sample and you measure the degree of oxidation in this particular oil sample. So we can do primary oxidation analysis for primary products such as peroxide. We can also look at secondary metabolites, hexanal, for example, or measuring malonyl aldehydes using the T-bars assay. So I'll be talking about all of this as well. And there is also a whole section on evaluating stability. This means if you have a certain type of oil, you want to determine how long the oil can go without onset of oxidation. And oftentimes, the measuring of stability is linked to testing um, antioxidants. So if we have a new antioxidant that we want to determine its impact in a food product, we can, or in on oil, we can take the food product with and without an antioxidant, or the oil with and without antioxidant, and measure peroxide value over time. So this is very important. And then the characterization of the lipid fractions, which we often do using GC methods and qualitative method by thin layer chromatography. So kind of this is a summary of what we're going to talk about. Don't worry, a lot of information, but they will all be broken down for you. Okay. I don't know why it's not going. Okay. So if we want to determine, let's say, peroxide value or oxidation within a sample, within a food matrix, the first thing you want to do is extract the oil. So not always you have an oil sample or a fat sample that you can analyze. Oftentimes you have a formulated product with certain amount of fat in it, and you want to determine the characteristics of the fat. I mean, how oxidized it is, for example, or how much free fatty acids do I have. So to do that, we really have to get the oil out and separate it from the rest of the sample matrix. So first step is removal of the oil, and it's often done by either batch extraction or semi-continuous extraction with the Soxit setup that you have seen in the lab. So the solvent extraction then can be done by different combinations of solvents. There's so many different unlimited combination. You learned about combining petroleum ether and ether. There's petroleum ether and diethyl ether, but there's also the combination of hexane and isopropanol, which is very common for extracting oils, chloroform and methanol. So you see the combination, for example, chloroform and methanol. Methanol is more polar organic solvent to help with the extraction of those polar lipids like phospholipids, for example. So there are different combinations, and some of these combinations work better for one type of food product versus another. And then once the fat is extracted, you want to remove the solvent so that you end up with just the oil to test. During this process, you have to be very careful not to overheat or to expose to a lot of light and oxygen. That's because it's going to change the characteristics of your oil sample. So you have to be very careful with the sample prep. Now, the physical characteristics here are mostly for your bulk oils or fats. So most of them are very characteristic. So characteristic to the different types of oils and fat. So there are tables, for example, for refractive index for different oils and fat. They use them to, for example, for identification purposes and for determining adulteration. So refractive index, for example, is related to the degree of saturation of the oil. Um, so it would tell you how, it gives you an indication of how saturated or non-saturated the oil is. And as I said, there is a refractive index for every type of oil that is standard. Melting point is also very specific. So it is the temperature at which changing from solid to liquid state. There are different methods for measuring that. And again, it's very characteristic for the type of oil. So these kind of measurements, again, it gives you an indication of the authenticity of the oil and if there has been any changes in the oil due to storage. Now, the smoke, flash, and fire point, why are they important? They're important especially for oils that you intend to use for frying. So the smoke point is the temperature at which the oil starts smoking. It gets too hot and it starts smoking. The flash point is the temperature at which you see a spark, almost a fire. And the fire point temperature and time that you actually have fire. Now, what does this tell us about the oil? So, for example, if you take virgin olive oil, do not fry with virgin olive oil because it has high percentage of free fatty acids. And this, the presence of free fatty acids, and if they get oxidized, you get volatiles. And these volatiles at high temperature will cause smoking, splash, and fire point. So when you choose your frying oil, you want to make sure that you choose one that has high temperature for smoke point or high flash point and high fire point. So, so some oils are meant for frying, other oils are not. And the more you fry with the oil, the more fatty acids you're going to generate. Because if you remember what I said last time, is when you have, let's say, your potato, it's high in moisture, and you put it in the oil, and moist water heat is going to cause breakdown of your triglycerides. So you get hydrolytic acidity, free fatty acids, and then these free fatty acids can oxidize. And the more you fry with that oil, the more you're generating free fatty acids and oxidative metabolites that are volatile that would cause low smoking point, flash, and fire point. Okay, so the cold test. We talked about cold test and cloud test. They're both can be used. Either one of them can be used to test the effectiveness of winterizing. And winterizing is the fact that you chill the oil so that you precipitate the waxes and you clarify your oil. So these tests are normally used to test the effectiveness of winterizing. And it's important for oils that are going to be used in salad dressing. You don't want them to look cloudy. That would be not desirable for consumers. So usually you store them in the fridge, and if they get cloudy, the consumers are going to think, oh, something is really bad about this. But it's only the fact of having waxes that didn't get winterized or removed from the oil. The solid fat index is related to how much fat you have that could be in a solid state at present room temperature. So the higher the solid fat index, the lower is actually your spreadability. So, and the lower is the solid fat index, the more smooth feeling you have in the mouth when you put that fatty substance in. Um, and it's usually measured. Um, I think it's just the fact that you try to melt what you have, let's say margarine or lard, and try to determine, or butter, and determine how long it takes to melt it or at what temperature it takes to melt it. And you can calculate, there is an equation to calculate solid fat index. Consistency and spreadability, usually this is, you can measure that with a texture analyzer. to determine, let's say, the force needed to compress the fat or lipid. So that relates to, again, how you're going to feel the smoothness and how easy you can spread that fat. All of these are described in more detail in your chapter 23. So if you want to learn more about them, you can read them there. But at least all the overview I've given you is just, I'd like you just to know the difference and when they are used and why they're used. Okay, so we're going to go into iodine value. And this was one of the methods you're going to do in the lab, as I said. So with iodine value, okay, so here's the thing. So when I ask you in a test, define iodine value, or what is iodine value, or what does it tell us, you have to, these first 2 points are very important. You have to know that iodine value is a measure of degree of unsaturation. And also you need to know the units. What is it about? What is the iodine value? The definition of it is the grams of iodine absorbed by 100 grams of sample. So you want to know this. You're going to do a lot of calculations in the lab. And once you do the calculation, it will stick. It's the grams of iodine absorbed by 100 grams of sample. So here's the reaction. You do not need to remember the structures, but you really need to remember the chemistry of what's happening. Sometimes I tell you, okay, tell me the chemical reaction. So tell me the chemical reaction, but you don't have to remember the structure. You want to know that we start off with something called excess iodine chloride. And excess is very important here, and that's why I marked it in red. So that means we provide an abundance of this chemical or reagent to react with the unsaturated fatty acids within your oil or fat. So if your oil is completely saturated, there is no double bonds at all, there will be no reaction. Okay, so iodine chloride is going to react with your double bond. And the iodine is going to, take reaction. You no longer will have double bonds. You have iodine, the C here, is going to have a bond with H, a bond with I. And then the other 2 bonds that are already there, so then the C is saturated. So all the 4 bonds are saturated or have a atom reacted with it. What is left here is all of the iodine chloride that did not react. So the way to go forward from there is react. The remaining iodine chloride is reacted with potassium iodide. You get iodine. The iodine in the presence of starch indicator, so now you will add your indicator in this reaction is starch, you'll get blue color. The more iodine you generate, the more you have, blue color. And we titrate with sodium thiosulfate. And we titrate until the last drop reacts with, well, what happens is the iodine reacts with the sodium thiosulfate to give you sodium iodide, your starch, and another compound. So what happens is when all the iodine reacts, at the next drop of the solution when all iodine reacts, you no longer have iodine to react with the starch, so the color goes to colorless. So you will be titrating here to colorless. You want to make sure in the lab to titrate until you see no color. So sometimes there is the very faint pink at the very bottom of your flask. Continue titrating but slowly so that you can capture the last drop that takes care of all of the color. So as you titrate, the color is going to go fainter and fainter and it becomes pink at some point. You're not done. Continue titrating. Now, how do we calculate the iodine value? Remember, it's grams in 100 grams of sample. So this equation is similar to the equation that I went over when I was talking about percent nitrogen in your sample, and we did a number of moles equal number of moles. So review that derivation so that you can remember this equation. It's the exact same equation based on titration. But here notice in Caldal, you were subtracting the blank from the sample. In this case, notice that we're subtracting the volume needed to titrate the sample from the volume needed to titrate the blank. Now tell me why. If you're paying attention, you will know why. Give it a thought. I know it's really boring to just talk into an empty classroom with very few people, and I don't see your reaction. I can't converse with you, but try. Anastasia. It's like if you do blank minus X, it'll be like the amount of iodine that reacts with the double bond. Exactly. Exactly. So that brings us back to the use of excess. So if the blank, that means you don't have any fat. So there is nothing to react with. So all of the ICL is available to react with the potassium iodide. So you generate the maximum amount of iodine. So you have the highest amount of iodine generated. So it takes the highest amount of sodium thiosulfate to neutralize the reaction. Therefore, the blank has the highest value. And the more unsaturation I have, the more ICL reacts. The less iodine is generated and the less volume of sodium thiosulfite I need to neutralize the reaction. Okay, so it's blank minus sample. So you need to know the chemistry behind this reaction so that you remember it's blank minus sample. It's not sample minus blank. Okay, and the normality is the normality of the reagent we titrate with, so sodium thiosulfate. So that would be the normality that you will be given when you are titrating with this reagent. Now, what is 126.9? It's the molecular weight of iodine. Okay, and we divide by the weight of the sample and multiply by 100. So to get grams per 100 grams of sample. Now we divide by 1,000 because remember, we are titrating, you're using milliliters, so you want to convert to liter, and you divide by 1,000. So you just have to remember or review the derivation we went over when I was talking about percent nitrogen for Kelvin. Then it will make sense again for you. It's a similar equation, similar derivation. Okay, so it can be used for fat characterization. When we determine the iodine value, you have also a table in your chapter 23 that gives you the iodine value of different types of oil. So we can determine the authenticity of the oil. It's a method that is used post-hydrogenation to determine the significance of hydrogenation. Another analysis that is important post-hydrogenation is what? I mentioned it briefly last time. So after you hydrogenate the oil, one thing you want to check, did you do it completely? You measure the iodine value. It should go down because you are hydrogenating, saturating the double bond. Another one that is important for a health reason and for labeling reason. Does that trigger something? Formation of something that is on the label. Al, trans fat. Exactly. So Incomplete hydrogenation can result in the conversion of cis to trans and having a trans fat. And so after hydrogenation, it's very important to measure trans fat um, content. Now, another thing is it can also indicate degree of oxidation. So let's say in the lab, theoretically, you will find a lower hydrogenation or lower iodine value for crude olive oil. So what does that mean? That means the crude olive oil undergone some oxidation that broke down some of its double bonds. So the iodine value theoretically can go down when the oil is oxidized. So in the lab, you're going to look at your data and try to understand, why do I have lower iodine value? Let me look at the peroxide value. Does it make sense? Is the oil more oxidized? So to connect the dots, you might want to connect the dots based on the results you get. All right, saponification value is another test that you will be doing in the lab. And again, it's another authentication identification type of testing. And there are values for different oils that you can find in a table in your textbook in chapter 23. For different types of oils, there are different saponification values or range of saponification values. So it is an index of average molecular weight of triglycerides in the sample. So we can use the saponification. What this is telling me is we can use the saponification value to determine average molecular weight of my fatty acids or triglycerides. So now, how is it defined? How do we define it? So it is defined by milligrams of KOH or potassium hydroxide required to saponify 1 gram of sample. So now you should know what saponification is because you've done it in the GC lab. Saponification is basically you're breaking down the triglycerides into fatty acids. And then they react with the salt. So what happens here, our alkaline is potassium hydroxide. And we have our triglycerides. So the equation here shows me 1 mole of triglycerides reacts with 3 mole, or 1 molecule reacts with 3 molecules of KOH to, with heat, in the presence of heat, the triglyceride bonds are broken. You end up having glycerol and potassium salt of fatty acids. So again here, notice the excess. So the excess means if I don't have fat, all of the KOH remains. If I have fat in there, some of the KOH is going to react with the fat component or the triglycerides, and there will be less KOH left. The remaining KOH, since it's base, we just titrate with HCl in the presence of phenolphthalein. So it will be kind of dark pink, reddish kind of color in the presence of KOH, the phenolphthalein is. And as you titrate with HCl, the color will faint, faint, faint until the last drop of HCl turns the solution colorless. If you look at the saponification value, remember it's milligrams of KOH per gram of sample. So there is no multiplication by 100 because it's per gram of sample. So we only divide by the weight of the sample. We do not multiply by 100. And you see here, you don't have in the denominator, you do not have a times 1,000. So the weight of the sample is not multiplied by 1,000 because we want the value in milligram, not gram. So you do not divide by 1,000. You use the milliliter and you leave the milliliter as milliliter. You do not divide by 1,000. So hence there is no multiplication by 100 and there is no division by 1,000. Everything else is the same equation. 56.1 is the molecular weight of KOH. Okay, so this is, and it's blank minus sample. It's the same situation here. Your blank doesn't have triglycerides, so all of the KOH need to be titrated with the HCl. So obviously the HCl volume here will be the highest for the blank. But when we have fat in there, you will have reaction with the KOH. So less KOH is left, less volume of HCl. Therefore, the sample volume is subtracted from the blank volume. You can interrupt for questions if there's anything you'd like me to repeat. All right, let's take out a piece of paper, and I'd like you to understand the supportification value and how we can use it to determine average molecular weight. This is a very common question that can come in a quiz or a final. So I need you all to do that. Now for a +2, Rachel. They already have a +2 assignment for Monday, I believe. So maybe next Wednesday, a +2 for calculations we're going to do now. All right, so we have a saponification value of olive oil. So that means we are determining, we have olive oil as starting sample. And the saponification value is 190 milligrams per gram of fat. What would be the average molecular weight of the fatty acid in the oil? And this will give us the average molecular weight of the dominant fatty acid, which is oleic acid, in olive oil. If the saponification value, let's not worry about the second half. Let's just worry about how do we calculate the molecular weight of, or the average molecular weight of fatty acid in this oil if I'm only given this one value, 190 milligram per gram of fat. Okay, here's what I want you to know and remember. Okay, I'm going to write behind me here. If I find something here. All right, so you want to remember in very simplistic manner, triglycerides, TG, one molecule or one mole reacting with 3 moles of KOH to give you glycerol plus fatty acid salt. Okay, 3 fatty acids. Okay, so triglycerides plus 3 KOH. Don't worry about this side, but you need to remember that 1 mole reacts with 3 moles. So what is the given? Okay. Or what is the question? I want to know the molecular weight, grams per mole, that reacted with 3 moles. So the molecular weight of KOH is 56.1. We get it from the previous slide. And I have 3 moles. So I have 3 times 56.1 grams per mole. So molecular weight to molecular weight. I have 3 times 56 grams, 0.1 grams per mole. I have 3 moles. So I multiply this molecular weight by 3. Okay, so I'm after X, which is the grams per mole, the molecular weight of triglycerides, which is grams per mole. You have to remember molecular weight unit. If you don't know the molecular weight unit, you might not know how to start this exercise. Okay, now what's my given? My given is 190 milligrams per gram of fat. So I needed 190 milligrams of KOH to saponify 1 gram of fat. So 1 gram of fat, okay? So 1 gram of fat needed, I have to convert to grams, the units, okay? So 190 milligrams is 0.19 grams. Okay, so that's my given. Okay, now you have this information. Another information that you have to keep in mind is when triglycerides in the presence of water, they get hydrolyzed into glycerol and fatty acids. So you have to remember, because you want to calculate average molecular weight of fatty acids, not just triglycerides. So from this information, you can get the average molecular weight of triglycerides. Now, how do you get the average molecular weight of one fatty acid? So you need to remember that triglycerides plus 3 molecules of water gives you glycerol plus 3 fatty acids. If I know the molecular weight of water and I know the molecular weight of glycerol, and I get the triglyceride molecular weight from this information, then I can subtract the molecular weight of water times 3 and the molecular weight of glycerol from the triglyceride molecular weight. I get the molecular weight of 3 fatty acids. Divide by 3, I get the average molecular weight of 1 fatty acid. So now what's the molecular weight of water? Is 18 grams per mole. What's the molecular weight of glycerol? I think it's 90 grams per mole. I think. 92? Where did you get that? You were very quick. Okay, 92. Okay, now solve. Take a minute with all of this information and solve. When you have an answer, let me know or type it in the chat. Maybe you want to see behind me. Why is it H2O? Okay, so this is the equation here, triglyceride by 3H2O, is not related to the titration or to the chemical reaction of the hydroxide, the potassium hydroxide. This is just when you have a molecular weight of a triglyceride, you want to know how that molecular weight came to be. Because in order to form triglycerides, you have 3 fatty acids that react with 1 glycerol. When they react, it's a condensation reaction. So you lose 3 molecules of water. So that's where this came from. It's just the makeup of the triglycerides. When 3 fatty acid reacts with glycerol, you get a triglyceride and 3 molecules of water. Okay, it's a condensation reaction. And to break it, you need 3 molecules of water to break it into 3 fatty acids and glycerol. This equation is just for you to convert or calculate the molecular weight of fatty acid that gives you the average molecular weight of triglycerides that you got from the given in this question. You're welcome. John, it doesn't seem right. Revisit your calculation a little bit. Yes. So Chrissy got the correct answer, which is 282.6 grams per mole, and this is the average molecular weight of oleic acid. If you look oleic acid, you'll get that molecular weight. Let's look at the calculations. Excuse me, I don't have the units here, but you have to remember to write your units. So this molecular weight of triglycerides, basically here you use the given, okay? So the given, if you're solving for x, so basically 1 gram times 3 times 56.1 grams divided by 0.190 gives you the x. Okay, this is how I solve it. I know that some of you would solve it differently. You go x grams per mole for 1 gram of sample, and then you have 3.56, no, 3 times 56.1 grams per mole with 0.190 grams. So you can take that ratio. So 1 grams of this particular molecular weight of triglycerides reacted with 0.190 grams of KOH of this molecular weight. So 1 mole to 3 moles. All right, and then you solve for X. And then what did you get for, okay, it's right there. So X grams mole per mole of triglyceride equal 885.8 grams per mole. Okay, so to get the average molecular weight of fatty acid, I need to apply this equation. 1 triglycerides react with 3 H2O or 3 molecules of water to give you 1 glycerol and 3 fatty acids. Okay, so I'm going just to erase this for a second. Now that I have how we got to the molecular weight of triglyceride. So I have now the molecular weight of triglyceride, 885.8 grams per mole plus 3 times 18 equals 92 grams per mole plus 3 fatty acids. I know it's getting small, you don't see it, but I'm just saying it out loud. Then I would take 885.8 grams per mole plus what's 3 times 18? 54. Plus 54 minus, bring the 92 over, so it becomes minus 92 grams. This is going to give me 3 fatty acids. Okay, what's the number of, what does this give me? Does somebody have the value? 885.8 plus 54 minus 92. 847.8. Now I divide this by 3 because I want the average molecular weight of 1 fatty acid. Now this gives me 282.6 grams per mole of fatty acid, which is exactly the molecular weight of oleic acid. Any questions about that? Yes, Anastasia.
So the first part is just kind of like a multimole ratio.
Yeah, multimole ratio, because exactly, is that the question? So the question is the first part, multimole ratio. Yes, because the ratio here, 1 mole reacted with 3 moles. And in 1 mole, how much do you have molecular weight, right? Because molecular weight is grams per mole. And 3 moles, you have 3 moles, so 3 times 56.1 grams per mole, so you get the molecular weight. That is multiplied by 3. And this is the given, that's 0.19 grams reacted with 1 gram of fat. So it's basically the chemical reaction. So you really need to remember that you have triglyceride that reacts with 3 KOH. If you remember this, you can put it side by side and remember 1 mole reacts with 3 moles. You just multiply the molecular weight by 3, and you know the given, whatever is the given, you have to convert to grams from milligrams, and then in 1 gram. So you always have that given. And you will be given the molecular weight of KOH, you will be given the molecular weight of water, you will be given the molecular weight of glycerol. So you have everything. But in order to solve it, you really have to remember the chemistry or the chemical reaction. And you really have to remember that triglycerides need 3 molecules of water to break down into glycerol and fatty acids. And you need to remember 3 fatty acids, when they react with glycerol, they give you triglycerides, and it's a condensation reaction. They give you 3 molecules of water. So if you remember this concept and the reaction, you'll be able to solve the question very easily. Okay. So free fatty acids. So in this case, you're measuring the free fatty acid that is liberated upon hydrolysis of triglycerides. So it is an indication of hydrolytic rancidity, either due to presence of lipase in a sample, or if it's a frying oil, due to the age of the frying oil. And it is also an indication of adequacy of refinement, because crude oil will have some degree of free fatty acid. When you refine them, you treat with NaOH, and the NaOH react with excess or fatty acid, gives you soap and water, centrifuge, you separate that from your refined oil. It's very simple. You're going to do it in the lab. It's a titration with the base. So the base is going to react with the acid, the fatty acids, and you can determine the percent fatty acid. Again, the same concept of this reaction, but note here, it's sample minus blank, because if you don't have fatty acids, you do not have any acids to react with NaOH. So in the presence of phenolphthalein, 1 drop of NaOH is going to turn pink right away. So the blank will be less than the sample. And the more free fatty acids you have, the more NaOH you need to titrate. And you titrate here to the end point that is pink. So in the lab, every time you titrate, for all of the other methods, is you titrate to colorless. In this case, we titrate for a pink color. And I say here, same principle as titratable acidity. Usually we learn about titratable acidity before fat characterization, but that lab is not going to happen in person, so that's why I moved up the fat characterization lecture. So, but when we cover titratable acidity, it's the same situation. You just titrate with base, determine total acidity, and because fatty acids are acids, then that's the concept of it. So the 282 is the molecular weight of oleic acid, and usually we put the molecular weight of oleic acid to determine free fatty acids, but if we want to look for a specific fatty acid, there are conversion factors. So if we want to determine it in a palmitic acid, we can multiply by 290. Don't have to worry about it. This would be given to you if you need to calculate it based on a specific fatty acid. And since it's a percentage, so you divide by the weight. Since everything is in gram and not in milligram or milli equivalent, so we have to divide by 1,000 to convert milliliters to liters, and you multiply by 100 because it's a percentage. So in this case, you divide by the weight, you multiply by 100. Okay, so good stop. Actually, it's a stop where I stopped last time. So we'll finish the rest on Monday. Okay, have a great weekend, everybody. Oh, there's a question when we will have our midterms back on Monday and Wednesday in lab. You will be given back your exams. Are they already graded? I just have to look through them quickly, review them, and then you'll get the grades and your exams back early next week. Just a second. Stop.